Good morning, everyone. My name is Afik Arong. Today, I'm going to present my research on the valorization of waste paper via chemical conversion for glucose production as a substrate in bioenergy process. Okay, next slide. Scope of presentation. In this presentation, I will cover the following point. First, first, the rationale of the study. Second, the methodology, the research and discussion, which include chemical composition, sugar concentration, and hydrolyzed U. Finally, I will present the conclusion and recommendation. Okay, next slide. Rationale and background. After flooding event, paper that has been soaked in water cannot be reused. It also decomposes very slowly, which often lead to improper disposal methods such as open burning, releasing greenhouse gas into the atmosphere. Waste paper, however, is a lignocellulosic biomass mainly composed of cellulose, hemicellulose, and lignin. This can be hydrolyzed into fermentable sugar, especially glucose, which serves as a key carbon source for bioenergy production such as bioethanol, biogas, or organic acids. Objective. First, to analyze the chemical composition of waste paper before and after alkaline pretreatment with 10% sodium hydroxide with 100 Celsius for 120 minutes, focusing on sharing in cellulose, hemicellulose, and lignin. And second, to determine the physical chemical property of the liquid hydrolyzed, including volume U, reducing sugar, total sugar, and Drake bricks. And finally, to evaluate the suitability of the hydrolyzed for fermentation and provide recommendation for quality control and process optimization. And next slide. Methodology. The first, simple sample preparation. Waste paper was cut dry to constant weight and analyzed for moisture. And second, alkaline pretreatment. Sample were treated with sodium hydroxide 10% weight by volume at 100 Celsius for 20 minutes under agitation. The solid fraction was depurated and the liquid hydrolyzed were filtered and cooled. Third, compositional analysis. Cellulose, hemicellulose, and lignin were quantified. Percent dry weight, mean plus minus SD before and after treatment. And then hydrolyzed analysis. Measure hydrolyzed U ml by G dry paper, reducing sugars with the NS method, total sugar with phenol sulfuric acid method, and Drake bricks refractometer at 20 Celsius. And finally, statistical analysis. Results were reported as mean plus minus SD and compare between pre and post treatment. Result figure 1 show the chemical composition before and after pre-treatment. Cellulose decreased from about 62% to 29%, hemicellulose from 17% to 8%, and lignin from 6% to 4%. This reduction confirmed that sodium hydroxide effectively disrupts lignin carbohydrate complex and solubilize hemicellulose, making cellulose more accessible for hydrolysis. Slide. Result Figure 2 and Figure 3. Figure 2 and Figure 3 present the sugar concentration and hydrolyzed yield. The reducing sugar concentration was about 342 milligram per milliliter, while the total sugar concentration reached around 422 milligram per milliliter. In addition, the hydrolyzed volume U was approximately 705 milliliters per gram of dry waste paper. This demonstrates efficient conversion of solid biomass into a sugar-rich liquid suitable for fermentation. Okay, next slide. Solid fraction after pre-treatment. Cellulose decreases from 61.56 to 29.36%. Hemicellulose from 16.7 to 8.44%, and lignin from 5.85 to 3.92%. This indicates significant breakdown of lignocellulosic structure and transfer of soluble carbohydrate into the liquid phase, according to Table 1 to 3, Figure 1 and Figure 1. Hydrolyzed yield was 705.33 plus minus 25.64 mg by ml by mg dry feedstock, reducing sugars 341.99 plus minus 16.6 mg by ml. Total sugar 422.13 plus minus 14.55 mg by ml, and Dirty Bricks 13.04 plus minus 0.7 bx, according to Table 2 and Figure 2 and Figure 3. Next slide. Conclusion and recommendation. The first conclusion: waste paper is a cellulose-rich feedstock suitable for alkali pre-treatment. 2. Sodium hydroxide 10% at 100 Celsius for 120 minutes significantly degrades lignocellulose. 3. The hydrolyzed contain high level of reducing and total sugar, although discrepancies in sugar quantification suggest further methodological refinement. 4. This approach enhances sugar release and demonstrates strong potential for valorization into bioenergy substrate, pending verification and detoxification. Recommendation 1. Performance balance reconciliation and express sugar as mg by mg feedstock and present theoretical yield. 2. Use HPLC to confirm actual glucose and identify minor sugars. 3. Apply neutralization and detoxification to remove inhibitors prior to fermentation. 4. Conduct optimization experiment. 5. Evaluate LCA and sodium hydroxide recovery for environmental sustainability. 6. Perform pilot fermentation prior to quantify ethanol or other bioenergy yield. Finally, I'm going to thank you my advisor Dr. Abdulsamad Sukel and Dr. Patama Pisapak, and they are from Yala Rajapat University, and thank you your attention.